So what about the solid gas boundary? Well, that is called sublimation. Have you ever heard of a sublimation printer before? Anybody have any sublimation shirts? Your shirt that you have on is probably a sublimation shirt. Does that feel? Can you feel that PlayStation logo on it?
No.
No.
It's a really comfortable shirt.
So that is sublimation ink. This is the way that works, okay? So sublimation is the transition from solid to gas. And then deposition is the opposite of that, going from gas to solid, right? So the way those shirts are made is they print that ink. Well, yours is high throughput, but you can do this at home. I have a sublimation printer at home. You can print ink on a piece of paper, right, on a special ink, and then you can lay that on a shirt, and you can heat it up. And when you heat it up, it turns that ink into, which is solid, dried, right, into a gas. And it goes into the shirt. And then when it cools off again, it goes back into the solid phase. And when it does that, it binds to not organic materials, but not like cotton, but it will bind to polyesters and things like that. So you can create fancy designs through this concept of sublimation, right? But again, sublimation is the act of going from solid to gas. And then going backwards, we call that deposition. And the deposition is very useful in materials chemistry. If we want to make thin layers of things, we use deposition all the time. So just like liquids and gases have a coexistence curve where they both exist at some pressure and temperature, solids and gases do too, right? There's a solid gas coexistent line where you can have a solid thing and a gas in equilibrium, and they will coexist at that temperature pressure. So what that means is that solids have a vapor pressure, right? Because even though it's a solid, it's in equilibrium with a gas, and as we heat it up, more and more particles can go into the gas phase. That's also why you can smell solid things, is because they have a vapor pressure. Some of the particles are able to go into the gas phase, right? We talked about melting already. Melting, freezing is solid liquid line, right? We've talked about heat of fusion in previous classes, but any of these transitions would have an enthalpy of transition. So delta H, remember, is defined as enthalpy from Gen Chem 1. Enthalpy is heat at constant pressure, and we use that like an energy term. It's just easier to measure heat, and so we usually say delta H instead of energy, because what's the difference? Well, energy would be how much heat and also how much work got put out in a process. It's really easy to measure the heat. It's less easy to measure the work. So we hand wave the work away in most situations and say measuring the heat is close enough, okay? So let's think about this for a second. If we go from solid to liquid, then this is called the fusion enthalpy, okay? If we go from liquid to gas, then this is called the vaporization enthalpy. And if we go from solid to gas, then that would be the sublimation enthalpy. The great thing about enthalpies is that they're what we call state functions. If you had my 105 class, then you probably heard those words before. But a state function means that it doesn't matter the path that you take to get from point A to point B. So if we want to know how much energy it takes to go from the solid to the gas, well, we could go from the solid to the liquid, and then from the liquid to the gas. And the amount of energy it takes to go solid, then liquid, then gas would be the same as going directly from the solid to the gas, okay? So we can say this right here. That allows us to mathematically say that the sublimation enthalpy of anything is just the fusion enthalpy plus the vaporization enthalpy, okay? And remember that delta H, we saw one of those earlier in the Clausius-Clapeyron equation. We said natural log P2 over P1 is going to be equal to delta H over R, 1 over T1 minus 1 over T2. And this is vaporization enthalpy here. All right, so this is one of the ways you can calculate vaporization enthalpy. You can look at what is the vapor pressure of something at given temperatures, and you can calculate delta H from that equation. Right? There are similar equations for the solid vapor line and the solid liquid line, right? They're a little more complicated and they're somewhat outside the scope of this class. You'll learn about those in physical chemistry if you take Chemistry 341.